Hello, Coach Travis here with another calculus video. So this is a video about concavity, or more specifically, it's a video about finding inflection points. So the idea is they've given us a function here, x cubed plus 8x squared plus 9x minus 7, and they want us to find where the inflection points are. So I guess they just want the x coordinate of the inflection point. Oh, well, that was nice. They gave us a hint. I don't know if you caught it, but this is not plural. So the hint is that we should only have one inflection point because they didn't make it either that or they just have bad grammar. But I don't, we'll find out. We'll find all the inflection points. Maybe there'll be more than one, but I don't think so. So, all right, so how are we going to do this? Okay, so the thing about concavity is that, okay, the original function is concave up whenever the second derivative is positively valued, and the original function is concave down whenever the second derivative is negatively valued. And so what that means is the places, the inflection points are the places where the concavity changes. So in order for the concavity to change, we need the sign of the second derivative to flip. We need it to either go from positive to negative or from negative to positive. So there you go. So the inflection points occur whenever the second derivative changes sign. So, all right, so what we need to do is we need to figure out where the second derivative changes sign. So, all right, well, let's find the second derivative. And so, all right, so let's see. So p prime of x is equal to 3x squared plus 16x plus 9, and then p double prime. So the second derivative is going to be 6x plus 16. So I'm finding the second derivative because it's the second derivative that tells me about concavity. So whenever I have a question about concavity or a question about inflection points, I think this is a job for the second derivative. Okay, and so now you say, okay, well, great, Travis, but what do I do with this? Okay, well, the way I always like to do these things is I like to make a number line. So here's our number line, and this number line is going to go along with the second derivative. And what I'm going to do is I'm going to mark on my number line, I want to find where the second derivative is 0. And you might say, well, wait, why do you care about where the second derivative is 0? Because I thought you wanted it to be positive or negative. Well, think about 0. 0 is a very if you're thinking about positive and negative, then 0 is a very special number, because 0 is the only number that is like both well, let me think. What is 0 positive or is 0 negative? And the answer is it's neither. So 0 is the only real number that is neither positive nor negative. So 0 is kind of like the boundary. So if I could find where this is 0, I'm going to kind of like know the cutoff place. So anyway, all right, well, let's find where this is equal to 0. So let's see here. So 6x plus 16 is equal to 0. So that means that 6x is equal to negative 16. And so that means that x is equal to negative 16 over 6, which is the same as negative 8 over 3. Okay, so that negative 8 over 3, that is the number that makes the second derivative 0. And so that's like the cutoff. The claim is that the cool thing here is that all the numbers to the right of this will be always positive or always negative. and the numbers to the left will be either always positive or always negative. So to figure out which is which, I just have to pick a number. So for example, if you think about what's your favorite number that's less than -8/3. And you can, again, you can say literally anything that's less than -8/3. So maybe I'll say -100, because, you know, -100, definitely less than -8/3. And now put negative, so again, now this number line is associated with the second derivative. So I want to put -100 into the second derivative. So if you put -100, if you take this -100 and you put it in for x into the second derivative, I don't actually care what number you get. All I care is whether it's positive or negative. And it's not too hard to see that it's negative. A -100 is going to make the second derivative a negative number. So I'm going to put a minus sign there to indicate negative. So the idea is that on this region, the second derivative is negative, and so that means the original function is concave down. And now let's test a point over in this region and make sure that there's a sign change. So now you think about, well, what's your favorite number that's bigger than -8/3? And I don't know, maybe you'll say, maybe, well, let's not go too crazy this time. Maybe you'll just say 1. 1 is a nice number and it's bigger than -8/3. So it's in this region. And now let's put 1 into the second derivative. If you put 1 into the second derivative, well, actually you get 22, but I don't even care what number I get. All I care is that it's a positive number. So the point here is now what this number line is telling me is that the original function, so I don't have a number line for the original function, but the fact that the second derivative is negative for all these numbers means the original function is concave down for all numbers less than -8/3. And the fact that this is positive means that the original function is concave up for all numbers bigger than -8/3, because the second derivative is positive for all numbers bigger than -8/3. So sure enough, what happened here is we have a change in sign. The second derivative changed from negative to positive at -8/3. And that's exactly what we need in order to be an inflection point. So I would say here my answer is x is equal to -8/3. And then, yeah, so there you go. So I'm pretty sure that's right, but what can I do here? I'm going to use the graph. I'm gonna verify my answer by using the graph. So let's see here. So, well, I mean, normally you would just verify your answer by pressing enter, but I didn't actually type this into the computer, so I'm not going to be able to check my answer that way. But I much prefer to check my answer on the with a graph anyway. Okay, so I'm going to erase all this now. If you need to see it still, you of course can just rewind the video. And now let's bring up the graph of the function. So there's the graph of the function. And so if we just had to guess, where would there be an inflection point? So it looks like the graph is frowning until maybe about around -3. And then it's smiling. So it looks like we have an inflection point near -3, near x is -3. And if I look at my answer, well, -8/3, that's about -3. So our answer does seem to agree with what I'm seeing here. And so that's pretty good. But I guess why don't we go ahead and draw it? if the x coordinate is negative 8/3, and then the y coordinate will be s of negative 8/3. And so you can see, okay, there's a point, there's the point right there. And I asked myself, does that look like it could be an inflection point? And the answer is, yeah, I think that definitely could be an inflection point. It looks like it's an inflection point because the graph is frowning until it gets to point A, and then it starts to smile. So, you know, like if the, excuse me, you know, if my algebra had told me that there was an inflection point at around 2, then the graph would tell me I made a mistake, because that is clearly not an inflection point. But whereas our answer of A looks like a pretty good inflection point. So I think we did a good job.